There are lots of ways to get energy, all right? And this is kind of an unusual way right here, where you're taking some peanuts and you're burning them. And enough energy by far is released that you can boil water, all right? And this process is what happens when you eat a peanut. In your body, the peanut's energy is released into your system, and it helps you move and think and breathe and do all the things that we do for granted. So a lot of pieces around us do have energy. It's not always obvious, like in the case of peanuts here, but it is cool. And you can see it's enough to boil water, which is no small feat.
If we combine one gummy bear, which is composed mostly of sucrose, with molten potassium chlorate, a violent reaction occurs. A surprising amount of energy is released by the reactants, and in the process, their atoms and molecules rapidly rearrange to form the products carbon dioxide, water, and potassium chloride. The reaction is said to be product-favored.
So in this kind of unusual reaction, a gummy bear is placed in potassium chlorate, KClO3. And KClO3 and the sugar in the gummy bear have quite an active reaction, as you can tell. And it's pretty cool. And again, this just shows the energy that is inside things like gummy bear. Now, the guy on the left there in that video, that little animation thing, he's using obviously a pretty large size gummy bear, and it's getting pretty crazy. It's kind of cool. The purple color that you kind of see there is from the potassium, and we'll talk about that more in the next section. But anyway, it just shows that once again, the foods we eat for a reason. We eat them for the energy, and the energy is something we can use then stuff to move around and breathe and all that kind of stuff. So again, thermochemistry or thermodynamics is just the study of energy exchange, and the energy can be heat, but there's other kinds of energy too. Pretty important section, not just for chemistry, but also for life itself. So the question comes, like, what drives chemical reactions? Like, how do they occur? How fast does it take for them to happen? Do all reactions occur? And if they don't all occur, like, why not? And that's a great question that chemists ask themselves. The first question as to what drives chemical reactions, what makes them happen or not, that's answered by the field of thermodynamics. And that's going to be what we're going to focus on big time in this section. However, the second question is also important, like how they occur and how fast. That's another field of science called kinetics. And kinetics is basically the study of how fast or slow reactions go. We're going to look at kinetics in Chemistry 222. But for right now, here in Chemistry 221, we're going to focus more on the thermodynamics, the driving forces behind chemical reactions, which I mentioned briefly in the last section. We're going to be looking at those in a lot more detail now. So when chemists sit down and think about, why does this reaction occur or why does this reaction not occur? That's a question for thermodynamics. On the other hand, because chemists, like everybody, are lazy and impatient, etc., sometimes it's nice to know why are they fast, are they slow, and why are they fast and they slow? That's really more a question for kinetics, which is something we'll talk about in Chem 222.
Thermodynamics determines whether or not a reaction is possible. A reaction that is not thermodynamically favored will not occur to an appreciable extent. Sand is not thermodynamically favored to change into elemental silicon and oxygen, and if undisturbed, no reaction will occur.
The driving force of a reaction is an important consideration in chemistry, and sand is essentially a mixture of silicon and oxygen. And in geology, you'll go into a lot more detail on the exact compositions and stuff like that. However, the important thing for us right now is that there's no driving force, if you will, for taking the sand back to silicon and oxygen, all right? There is a driving force to take the raw silicon and raw oxygen and make sand, but there isn't a way to go back. So this reaction, thermodynamically, is not favored. All right, we would not expect the sand to go back into silicon and oxygen.
Reactions that are favored both kinetically and thermodynamically do occur. Paper, for example, will burn quickly in air if ignited.
Taking a piece of paper and giving a spark to it will definitely cause it to catch on fire and burn, all right? This is an example of a reaction which has a driving force. Thermodynamics wants it to go, like we see it actually go, and that's cool. In addition, this is a fast reaction, all right? You can see the paper burn right in front of your eyes. Some reactions will occur, they have a driving force, but they're really, really slow. So the burning of paper is, first of all, thermodynamically favored, which is really what this is about, but it is also kinetically favored. It's going to be fast. It's not going to take many lifetimes to make it burn.
Kinetics controls the rate of a chemical reaction. Even if a reaction is thermodynamically favored, if it is not also kinetically favored, it will not occur in an observable timescale. Diamonds are thermodynamically favored to turn into graphite, but the reaction is so slow, it never occurs. Some reactions take more time than others. Iron nails react with oxygen slowly, producing rust over a period of months.
Both of these reactions are thermodynamically favored to occur. And what that means is that diamond is going to turn into graphite on the left, and the iron nails on the right will turn into rust, which is basically an iron hydroxide kind of compound. That's going to happen. All right. On the other hand, the difference between these is the one on the left, diamond's going to graphite, takes thousands of years. And if you heard this and saw this, that, oh my gosh, diamonds are going to go down to graphite. Graphite is basically what's in your pencil when you write on it. You might be thinking, oh my gosh, I got to go sell my diamonds, man. Because diamonds are really expensive and graphite is obviously really cheap. But please do not go sell your diamonds if this is something you were considering. The process of taking diamonds to graphite takes thousands upon thousands of years. So the diamonds you have right now will be available to your children's children with no problem. All right, it's not going to happen anytime soon. So diamond going to graphite is thermodynamically favored. There's a process by which that's going to happen, but the kinetics are so slow. It takes just an incredible amount of time for it to happen. So we, with our lifetimes as humans, don't have to worry really about diamonds going to graphite. On the other hand, if you leave your iron nails outside and it rains or something like that, yeah, it's going to turn into rust, all right? It's an interesting process. It goes through several things. The final rust is like a Fe2O3, an iron 3 oxide kind of compound. But anyway, that's a process which is thermodynamically favored, i.e. the iron nails will go to rust, but it's also relatively fast, all right? It does take a lot longer than the piece of paper burning, but it will happen. It might take months. So you can see why kinetics can be really important. Burning paper really fast, making the iron nails rust. You can watch it. It takes a couple months and stuff, but it's possible. On the other hand, diamonds going to graphite, that will occur, but man, it takes a long time. So again, kinetics will answer the questions of speed, like why some reactions are fast and some reactions are slow. Thermodynamics is basically a yes or a no, a thumbs up or thumbs down. And the paper burning, the diamond to graphite, and the iron to rust, all of those are thumbs up. Those are all reactions that are going to go. But the speed is so drastically different, it's almost like you can basically consider the diamonds to not go to graphite in our lifetimes. And that's kind of an important consideration. There's lots of reasons why thermodynamics claims that reactions are product favored, and we've seen some of these reasons already. But a lot of times if you form a precipitate or a solid, that is a good driving force that allows thermodynamics to say, yeah, let's do this. Then that's the precipitation reaction we looked at in the last section. If you form a gas or if you form water, for example, in the gas forming reaction or the acid-base reaction, those are also driving forces that allow thermodynamics to declare a reaction to be product favored. That's really cool. Electron transfer in a redox reaction is another possible reason why a reaction can be product favored. So, for example, batteries are all reactions, chemical reactions that are going to occur, basically. Those get the thumbs up from thermodynamics. And in general, this is important, if you have a reaction that transfers energy to the surroundings, so from the inside to the outside, if you will, most of the time those are going to be product favored reactions. And this is a conversation we're starting here that will last all the way through Chem 223. In thermodynamics, and this is more than just chemistry now, this is going to be physics, chemistry, engineering, basically all of the world, there is something called the conservation of energy. Now, we've already seen the conservation of mass. Mass cannot be created or destroyed. Conservation of energy is similar, but for energy. And the conservation of energy, the total energy is unchanged in a chemical reaction. So energy cannot be created or destroyed. When all the scientists look at all the processes that can happen, there are essentially two forms of energy, and those forms are heat and work. And heat gets the symbol Q, and work gets the symbol W. So the first law of thermodynamics, which is important for not only chemistry, but all of physical science, just says that, again, energy can't be created and destroyed. And all of the energy, the change in energy, is going to come from heat Q and work W, all right? So this is really important. I mean, everything we do as human beings in the world falls under the first law of thermodynamics. You can't create or destroy any energy. And all that heat and energy, or all that energy, has to come from heat and work. And chemists usually focus on the heat part much more than the work. In physics, you'll look, and maybe engineering, you'll look more at the work part when you want machines to do your things for you. Chemists are really interested in the heat. So we're going to use this symbol Q a lot to represent the heat of a system, all right? And when we talk about heat, because the work is usually not important to chemists, heat and the energy are essentially the same. So remember that. We're going to see a lot of things with Q coming up. And most of the time in chemistry, Q, the heat, is the energy of the reaction we're looking at. Unless you're doing things with work, that's a pretty good assumption. There are ways to measure energy, and some of these you've probably heard of, and maybe some of them you haven't, but no big deal. The initial way that people used to talk about energy was through what's called a calorie. Now, calorie here has a little c. It's C-A-L, but it's little c, and that's important. We'll talk about that in a little bit. I call the little c calorie a science calorie. So a science calorie is literally the heat required to raise the temperature of 1 gram of water by 1 degree Celsius, all right? And James Joule there in the lower right was one of the big founders of a lot of the energy studies we're going to talk about. He has a very cool beard, if I might say so, but that's neither here nor there. So the science calorie has a little c, and it's literally the energy required to raise the temperature of 1 gram of water by 1 degree Celsius. 1,000 science calories is equal to a kilocalorie. Kilo is just a metric prefix, so 1,000 meters is a kilometer. 1,000 science calories is equal to a kilocalorie. And kilocalorie is a lot of times abbreviated as kcal. And in many countries, if you look at the sides of food and drinks and stuff, they will list their energy in terms of kcals, kilocals. Now, in the United States, usually, instead of using kilocals, they will use the capital C calorie. And I'm going to call that a food calorie. So a food calorie is essentially equal to 1,000 science calories. You can see why calorie is a little bit weird. And the capital C calorie is what in the United States you see on foods and drinks when you look on the ingredients. It will list how many calories are in a cookie or whatever you're eating at the time, all right? So 1,000 science calories equals a food calorie, and a food calorie is a kilocalorie. Calories, though, are really confusing because there's a science calorie and a food calorie, and not everybody capitalizes the food calorie, which is okay, all right? Scientists were tripping over degrees Kelvin, I think I told you in chapter 1. So, this shouldn't be a surprise, right, that science are freaking over capital C, little c calories. But anyway, instead of the calorie or the food calorie, what we're going to use in this class for representing energy is the joule. And it's named after good old James over there. James is really cool. A joule is another type of unit of energy. And 4.184 joules equals 1 science calorie. Okay? So that's going to be important. 4.184. You should memorize 4.184. And we'll see why more so than this example in a little bit. But if you need to translate joules back to science calories, no problem. 4.184 joules equals 1 science calorie. Now, because a food calorie is 1,000 calories, a food calorie is 4,184 joules, all right, if you're curious, and that's fine. We will use a lot of kilojoules, and a kilojoule is just 1,000 joules, all right, so you can do that. Joule is what they call a derived unit. So you can actually break the joule down into kilogram meters squared per second squared. And this might be more helpful later than it is right now. But like the kilogram or the gram, for example, is the base unit of mass. Meter, of course, length, time would be seconds. Joule is what they call a derived unit because it comes from other kinds of units. And this will come back to help us later. But don't worry about that right now. Just realize that basically from here on in Chem 221 through Chem 223, we're going to use the joule. And it's 4.184 joules per science calorie. And if you want, you can translate your food calories into it, which is kind of fun. So yeah, there's all kinds of connections to the real world. There are two types of energy when it comes down to chemical systems. There's what they call the potential energy and the kinetic energy of a system. Let's consider a bungee jumper. Now, I admire these people, although honestly, they kind of terrify me because I don't know, the heights thing maybe, I don't know. But anyway, a bungee jumper is just someone that jumps from like the side of a bridge with like a rubber band basically on them, and then they bounce. They don't actually hit the ground, but I'm sure it is quite exhilarating. So imagine that person there, especially the dude in the white pants. He's like on the edge of that little shelf thing right there. So that person is about ready to jump. That person has potential energy. Potential energy is sometimes due to where they position. So like he's about ready to fall. That's some energy that he's ready to use. You can also have stored energy though as well. And in an ionic compound like sodium chloride, those sodium and chloride ions are attracted pretty strongly to each other. Electrostatic energy. And if you know how to do it, you can break that energy apart and make it do other things. So potential energy is like energy that's stored within the system. It's ready to go. All right. And that's kind of cool. Now, electrostatic energy is again just a fancy name for the positive negative ion energy. You can also have, for example, gravitational energy, which is probably more what the bungee jumper has than anything. And there's definitely some nuclear energies that we're going to talk about in Chem 222. But right now, just realize that potential energy is like energy within bonds. And until you activate it, it doesn't necessarily do anything. Kinetic energy is the energy of motion when you actually no longer are having it stored inside or you're not on the edge of that little cliff and you actually jump, all right? So kinetic energy is like active energy. Potential energy is kind of like stored energy, and kinetic energy is active energy. Now, there's many types of kinetic energy, 3 forms specifically. The most common one probably to you is translational kinetic energy. And this is the kinetic energy equals 1/2 mv squared. In physics, this is an equation that's used a lot. If you haven't taken physics, then don't worry about it. Kinetic energy 1/2 mv squared, where mass is the m and v is the velocity, the speed, the meters per second or miles per hour or whatever kind of units you're using. So when that person jumps from the bungee platform there, they are turning their potential energy, which was the energy of their position, into translational energy, the energy of movement. And that's pretty cool. Now, as a molecule, molecules are moving all the time too. They usually have a velocity and they have a mass, so you can calculate their kinetic energy as well. Vibrational energy is like literally like going back and forth. And I like to think about this as dancing in place. So you're not moving around while you're dancing, but you're like moving your arms and you're wiggling your waist or whatever, all right? And in molecules, you can see that little thing right there. The little atoms are moving around. They're dancing, man. Woohoo! And vibrational energy is a type of kinetic energy. It takes energy to do it. You're not breaking any of the bonds in the molecule, you're just making them kind of vibrate back and forth. And this is something that happens all the time in molecules. As long as you are above 0 Kelvin, you're going to have some vibrational energy, at least in almost all situations I've ever seen. But finally, there is rotational energy as well. And rotational energy is when literally you rotate. So imagine you're dancing in place, all right? You're not moving, but you decide to rotate. You decide to move in a circle, all right? That's what rotational energy is. So you can rotate yourself in a circle without moving, all right? And that would be rotational energy. And molecules do all three of these almost all the time. The translational energy is just natural movement going from point A to point B, but they're also vibrating. The little bonds inside are moving, and they almost inevitably are rotating around like crazy too. So a lot of energy in any chemical sample, that's for sure. Kinetic energy depends on temperature. So you can imagine that if it was really cold outside, you wouldn't probably want to dance that vigorously. On the other hand, if it's a nice summer night, and it's feeling good, yeah, you'll probably be more into dancing. Yeah, you can tell maybe I like to dance. It's one of my secret things. But anyway, I digress once again. Kinetic energy does depend on temperature. All right, so the warmer temperatures, you're going to have more of these kind of movements. The lower temperatures, you'll have less of these kind of movements, and that definitely applies to molecules as well. In energy, we also talk about the system and the surroundings, and this is an important thing to think about too. No chemical system is isolated from the universe, all right? You always have interactions between the chemicals that are reacting and the outside, and the outside can mean a whole bunch of different things. It can mean a solvent, it can mean the outside air, it can mean a whole bunch of things. So when we talk about the system, those are the molecules that are actually reacting, the ones that we're studying, all right? So in this example, in the piston, you've got hydrogen and oxygen, and probably they'll come together to make water, all right? So that's the system. That's the interesting part usually to the chemist. But the surroundings is everything else. Now with a piston like that, that's probably a closed system or an isolated system. But the energy that's going to be created from hydrogen and oxygen coming together has to go somewhere, and it's going to go to the surroundings. So in the piston or in the thermos in example A, or the container in number B, the energy will go to the walls of the container. You could actually measure the heat going up a little bit if there was enough of it, which is really cool. Now, an open system just means that the energy is able to go into the atmosphere. And this is also, of course, very common. So if you have hot soup, the steam is some of the energy being released into the surroundings, and it allows then for the smells and stuff to get inside there and stuff like that. So the system is like the molecules that are actually chemically reacting, and the surroundings is basically everything else outside. It might be just the container, it might be the air, it could be all kinds of different things.